So what have we done so far? We've seen the vanilla pattern matching. That's the KMP. We've seen that if you just want to find whether your pattern exists in the text exactly as it is, and it's one-dimensional, you can do that in linear time. Then we said, okay, but what happens if you want to do it in 2 dimensions? So we saw that you can do it in 2 dimensions, and we used the dueling algorithm for 2 dimensions, and that was at that point, we can do a multi-dimensional pattern matching without dependence on the alphabet size. So we're happy. Then we moved on and said, well, all of these were sequential kinds of algorithms. If you actually want to do it in parallel, in other words, where you want to only do local operations and yet find your pattern, can that be done? So we saw the renaming technique, and that worked for us, and so we're very excited, and we're moving on and saying, well, what else is out there in the horizon? So what's out there today is something that we already hinted at, is pattern matching with don't care. So we take this special phi, the character phi, which is not in the alphabet. So that's going to be a symbol that is not an alphabet symbol. And we add that symbol both to the text and to the pattern. So we may have this symbol sitting there. But because it's not an alphabet symbol, it doesn't behave as alphabet symbols behave. So, in fact, so this is how it behaves. We have our input is going to be a text, P0 to Tn, a pattern P0 to Pm. And these T's and P's are either alphabet symbols or they're the don't care character. Now, what's our output? So we need to find things. In pattern matching, what you need to find is all the locations where 1 for 1, the text symbol is equal to the pattern symbol. If it equals through the entire pattern, then we say, okay, the pattern starts here in the text. But with the don't care, we call it don't care because we really don't care what's the symbol across from it. It could be that that symbol is A or B or C. I don't care. Whatever it is, the don't care symbol is happy with it. So, therefore, our output is all the locations J in the text where either Tj is equal to P0, Tj plus 1 is P1, Tj plus m is equal to Pm, which is the regular vanilla pattern matching that we know, but it could be that Tj is not equal to P0, but it's actually equal to don't care. Or it could be that P0 is the don't care, so therefore it matches everything. So in fact, when you're saying that you have the don't care characters really match everyone. They match whoever is in front of you. Now there are many uses for that, and one of them we saw. If you want to linearize something that's 2-dimensional, then you can pad it up with don't cares. And then you can look for a pattern in a text that's a string and not 2-dimensional. But in fact, it's even better than that, because suppose everything that we looked at until now, a string is a string, but the 2-dimensional patterns we looked at were basically rectangles. But what happens if you're looking for something that looks like this? Okay, so here this is red inside, but you don't care what's the outside. So here's a 2-dimensional object that we need to match. This like a red circle or wheel, but we don't really care what's in there. So what kind of even if we put it inside a rectangle and do a 2-dimensional matching, so fine, we know what's in here, but what is the color or what are the symbols that we're going to put here in the pattern so that we'll find it? And the way to do it is to actually put here don't cares. So we can make a rectangle. Everywhere where we don't care what's there, we put in a don't care. And And then you can look for it. So in fact, people have done that. So that's another use for don't care. And then there are other uses as well. In biology, for example, they may say, okay, I have a gene, and I want to find all the places where that gene is, or a protein. I have some sort of a protein, I want to find that protein in the DNA. However, it's not a specific protein I'm looking for. I'm looking for some types of things. I want something that looks like I have this kind of loop here, and I don't care what else there is, and on the other side there's this kind of loop. And whatever happens here, I don't care. So if I don't care, and I look for it, so pat it with don't cares. And since I'm always taking this opportunity also to tell you about far-off exotic places, so in the Hebrew language, for example, the vowels are not part of the alphabet. So you have an alphabet that and that's mainly the consonants, but the vowels themselves are added symbols. So if you want to say, for example, so if you want to say noon, so noon is called tzahoraim, this is like this, but the vowels aren't there. So in order to put the vowels, you have these special symbols that you add underneath, and then you know what the vowel is. Now, it's actually quite confusing for people who are beginning to learn the language, because they see, imagine that you see in all the words that you read just the consonants and not the vowels. So write it like that, it can be confusing. Now, when you get used to it, you fill it in. But there are some words where if you add different vowels, then the consonants are the same. The vowels make it a different word. So that you need to understand from the context. But that's how it goes in Hebrew. However, one of my pet peeves is how some of these vowels are actually pronounced. Because there are, since the Jewish people have been all over the world, the pronunciation has diverged. And so people who come from different countries have different pronunciations of the vowels. So the same vowel that is written like that, so the Eastern European Jews would say O for this vowel where they see it. The Sephardic Jews or the Oriental Jews would say A, and the Yemenite Jews would say E. So the same symbol, people pronounce in a different way. However, there are also vowel combinations that are interesting. So suppose, for example, that I want to find out in the Bible all the words that have this vowel followed by this vowel. At that point, I'm going to use don't cares, because the way that you're going to actually represent the language, you're going to put the letter and the vowel following it, and then the other letter and the vowel following it, etc. So if you want a certain combination of vowels, you're going to look for the don't care vowel, don't care vowel. Because I don't care what consonant there is, I want to know what are the words that have this combination of vowels in them. So this is something that's quite important sometimes, and the use that we've actually used don't care for. So I think that at this point I've convinced you that it's not unreasonable to say, I want to do pattern matching with don't cares. Now there's also something else that's funny here, because you would think, and that happens many times in life, you would think that if you say, I know how to do pattern matching exactly when I want to match things. So when I say, well, for some of these, for this symbol, I don't care what it matches, it should actually be easier, because it's more slack and it's more relaxed. And I really match everyone, I'm not so rigid. So it should be easier. And the surprising thing is that it's not. So here's an example of matching with don't care. Suppose that our pattern is B phi B, and our text is A phi A phi A phi. Well, exact matching there isn't here, but there are two places where the B phi B matches. One of them is here, because the phi matches the B, the phi of the pattern matches the A, and the phi of the text matches the B. So in this location, the pattern actually matches. And similarly, in this location, it matches. On the other hand, if you put the pattern here, it's not going to match because A does not match B. And similarly, if you put it here. So this is the pattern matching with don't care. Now, I think I even said it to you, but I always say that the first thing that you always do whenever you're presented with a problem is think of what you know how to do, the naive way. Or if you already know how to do something in a specific way, try what you know. So we do know already both the witness and the automata methods. So let's see if we can actually impose it on this problem and see if it works. Now, the witness and automata methods, in fact, work for other matchings than the exact matching. And we probably will see examples of that also. We'll see parameterized matching, for example. So they do work. So maybe it works here, and at that point we're done, and we can move on to the next topic. So it's not like we don't have topics waiting there in line. A good friend of mine, Alberto Apostolico, who was one of the founders of combinatorial pattern matching, he passed away about 2 years ago. But he had a story. For many years, he was a professor at the University of Purdue in Indiana, in the United States. And so he said in Purdue, they had a group of people who used to, their thing in life was to factor large numbers because they were in the cryptography group, and so they used to factor large numbers. And it was a group of these crazy hacker mathematicians, and they would look for all kinds of fast ways to factor huge numbers because that's one of the things that you need if you want to break codes or something. So factoring large numbers was their thing. Now the universities always want good public relations. So they wanted to tell the whole world, look at the great stuff that's happening in Purdue. So they brought the media over to talk to these guys. Now, my friend Alberto, who was a very colorful character, and he used to tell stories in a very colorful way. So he said the guy in charge of that group was really, didn't look very professorial. He was always with these shorts and t-shirt that wasn't entirely always clean, and never combed his hair. He had this long hair, didn't shave too much, and so he was always just in love with his work. So these people, they come over, they take pictures of all the computers and of the group, and then they interview him. And they ask him, so why do you factor large numbers? So he says, at this point, so Alberto says, his eyes became big and manic, and he says, because these numbers are just there, wanting to be factored. And no sooner do you factor one, and another one pops up and wants to be factored. So the university was very unhappy with that interview when it aired on television. They didn't come out looking so good with this crazy guy saying, these numbers want to be factored. So I remember that because I'm saying, well, we have these topics just waiting to be taught. So no sooner do we finish one topic, and there's another that pops up. All right, so let's see if witness or automata methods help. Now, I said that they help in many cases, but all the cases that they help, there is transitivity. And this transitivity, the people who've been here from the beginning already, they have the big T in their mind. They know about transitivity. But let's see what happens here. Suppose this is my pattern, A phi B B. Now, when we're building the witness table for W2, so for this location, there's really no discrepancy in the intersection. So in the overlap, they agree because A is equal to phi, P is equal to B, and B is equal to B. So they agree on the overlap. And if they agree on the overlap, so the witness table is going to put here a star, since they agree on the overlap. There's really no problem. If we're going to be building an automaton, and we're looking for the back arrow from here, we're going back, well, this is the longest prefix, that's a suffix. So we're also, because this is a suffix, so we're going to go here. That would be the longest prefix, that's a suffix. What it means in all these cases is that we're not going to recheck that. So if we ever need to shift, we don't recheck it because it agrees. We know already that everything is good. The star in the witness table says everything is good. We're not going to kill one of them. However, let's look at the case of the text and see if we're not going to be missing something because of that. And the point is that we are. Because if this was the text, ABB, ABBB, okay, so we have a match here. And if the, let's now go back to the automaton. And if the, and if there's no, and if here there's no match, we're going to follow the fail link to the largest prefix that's a suffix. In other words, we're going to assume that everything is okay up to here and continue. And we may say, okay, here's a match. But is there a match? Look, this A actually does not match the B. And so we're going to be mistaken. We're going to actually declare that there is a match and there isn't. If we're going to build an automaton the way that we know how to build an automaton and then follow it in the way that the KMP algorithm does. The same thing would happen with a witness table, because the witness table is going to leave both of these alive because of the star, and therefore it would assume that if this is good for this one, it's also good for this one. But it's not. Because even though we put a star, they don't really agree on the overlap. So I can't assume that everything in the text is good for everyone that's left. So for both of these cases, it's not going to work. But you can see here why it's not working. Because the phi matches the A here, and it matches the B here, but the A doesn't match the B. And both of these, the witness table and the automaton method, both of those methods, we did the pre-processing on the automaton, assuming that if I match the text, then whatever I decided for the automaton is going to be good for the text, or whatever I decided for the witness table is going to be good for the text. And the reason we could say that is because of the transitivity. But here there's no transitivity. So if something is good for the automaton, it's not, and if this is good for that, for the automaton, for the pattern, and the pattern matches the text in some location, it doesn't mean that the shifted pattern is going to match the text. And so it's not working. So this actually puts us in a deep sorrow, because we're standing there and saying, oh no, so what are we going to do? Are we really going to pay O of NM for solving something that is so simple? Well, the answer is no, because now we're going to come to a new method. So it's not anything we saw so far, but it's really a new method called polynomial multiplication. The first time it appeared in print in the literature was by the Fisher and Patterson paper of 1971, but although the truth is that even though you look at me, you think that I was alive and active in 1971. Alive I was, but I was too young. But people who were not too young then will tell you that this concept was a folklore even then, before that paper. What they did in the paper was they actually proved it, but people knew that you could use the concept. So what's the concept? Let's go back to polynomial multiplication, or in this case even we can say regular multiplication. So think back now to second grade when we were sitting there in class so eager and the teachers were telling us how to multiply large numbers. So the teacher told us that suppose you have this number, these are digits, and you want to multiply it by this number, so the b's are the digits of the number that we multiply by. So what did the teacher tell us? They say, okay, you multiply the b0 by the a4, then b0 by a3, b0 by a2, b0 by a1, b0 by a0. And then you shift and you do the same thing with the b1, b1a4, b1a2, b1a1, b1a3, b1a2, a1 and a0, and then the same shift over once more, and you multiply the b2. So that's what the teacher told us. And then they say, add up the columns. Now, they even added an extra confusion to the issue, and they said, well, you have a carry, because if what you multiply is not one digit, then you move the carry over and you have to add. So that's all that they taught us in second grade. Now, as an aside, I have to tell you that I always had a problem. That in second grade, I had a problem with all of that, and for two reasons. The two reasons that I had a problem with it was, one was that they were telling us about this multiplication. So the teacher said, okay, you have this function, multiplication, and you do it. And they even made us learn by heart the multiplication table from 1 to 10. They probably made you learn it by heart also. I had once a student from, when they came in from the old Soviet Union, there was an influx of those students, and they said to me, what, you are complaining about 1 to 10? In USSR, they forced us to learn it from 1 to 20. So there they do everything better. So they forced them to learn from 1 to 20. And 1 to 20, notice, is not just twice as much. Which brings me to another story. Once there was a group of soldiers that the commanding officer was unhappy with them. Now these soldiers were what we call atuda. First they do university, then they go to the army. But they were doing basic training at the time. And the commander was very unhappy. And he says to them, okay, so now, because you were not good, you're going to now have to dig here a hole 2 meters by 2 meters by 2 meters. So one of them says to him, listen, it will be a lot easier for us if we can work in parallel. So do you mind if we dig 2 holes of 1 meter by 1 meter by 1 meter? He says, fine, that's okay. So, but to get back to that, so they forced us to learn by heart the multiplication table. And they never proved that this is actually a function. So they're telling you, okay, you have a multiplication function. How do I know that it's a function? It's not until I learned piano arithmetic in the university that I actually got the proof that the inductive functions exist and are unique. But at the time, what? You make someone learn by heart something, he doesn't even know that it's a function? So that was wrong. I think it was wrong, methodically wrong. Prove to us that it's a function, and then that it exists, that it's unique, and then make us learn it by heart. Okay, so that was the first thing. But the second thing that I said is this entire thing with the carry is actually confusing. So why not start with polynomial multiplication rather than integer multiplication? Because in polynomial multiplication, if these are your coefficients of the polynomials and you multiply them, then this is exactly what you do, but there's no carry. You multiply, you add, and those are the coefficients of the result. So it's a lot easier. So why not start in second grade, teach polynomial multiplication, then you don't need to worry about carry, and then move on to the more complex cases of regular multiplication. So I had, both of these were problems, but this was a thing of the past. I'm sure that all of you had the same kind of problems when you were in second grade. But as far as we're concerned, and I had a third problem, which we'll get to in a minute. But these two problems I had. But why am I telling you this? Because I found an audience that I can vent about my math teacher? No, I liked my math teacher in second grade. But it really helps us, this entire idea. Why does the idea help us? Because let's define, I'm going to make this a little bit smaller. And I'm going to raise the screen. So the reason that I'm saying that this actually helps us is the following. Okay, so take a look. We multiplied things here. But what are we concerned with? We're concerned with pattern matching. So let's assume that this is our text. And these are the symbols of the text. And let's assume that our pattern is B0, B1, B2. And so notice that what we have here is the pattern but reverse. Now this reverse is only technical because of what happens here with the multiplication. However, if we're looking at this, then now what do we ask ourselves when we're looking for pattern matching? So if I'm asking if B0, B1, B2 matches the text, then what I'm really asking is, if I put here B0, B1, and B2, is this equal to this, is this equal to this, and is this equal to that? That's the question that I'm asking. But take a look at the magic that happened here. Because if you look here at this column, what do we see? We see the A0 and the B0, the A1 and the B1, and the A2 and the B2. So they're exactly juxtaposed in the kind of matching that we want. So that's what we want happening. We're asking if B0, B1, and B2, if we put them next to the A0, A1, A2, if they're equal. Well, the multiplication, it doesn't ask if they're equal, but it puts them next to each other. And that's already the first important step for us to notice. They're next to each other. But in pattern matching, we are not satisfied with that because we actually are asking more questions. We also shift B0, B1, B2, and we ask, is A1 equal to B0, is A2 equal to B1, and is A3 equal to B2? And lo and behold, look at this column. And they're exactly juxtaposed in the way that we want. Wow, does this continue? Yes, it continues, because if we shift even more the B0, B1, B2 over here, then what we get is this column. B0 with the A2, B1 with the A3, and B2 with the A4. So wow, I mean, this is the kind of thing that at this point you feel like you're in one of these magic shows and I pulled the rabbit out of a hat. Look, in the multiplication, what we have is what we have happening just by multiplying the shift that pattern matching does. Pattern matching actually shifts these things, and it's happening here. So this actually makes us all very excited. And the question is that you'll ask is, well, but you're not asking if it's equal. You're actually multiplying. Okay, fine, so we're multiplying. So let's do the following. Let's define A times B to be equal to 0 if A is equal to B. I'm now defining the multiplication in a different way, where A times B is 0 if A is equal to B, and 1 if it's not equal. So that's how I'm defining it. If I'm defining it that way, then what is going to be the result of this column when I add them all up? Suppose there is a match. What's the result? 0. And if there isn't a match, the result is non-zero, because some of these multiplications are going to be 1. And in fact, not only is the result going to be non-zero, but the result is going to tell us something. It's going to tell us how many mismatches do we have. So wow, this is incredible. Okay, and we get the same thing for the second location. If there's a match, it's a 0, and if not, we get the number of mismatches. And the same thing applies to the third column. So all we need to do is multiply and look at the results. Everywhere where there's a 0, we say we have a match. Everywhere where there's a non-zero, we say we don't have a match. Okay, but we started all this not in order to find another algorithm for pattern matching. We did it because we had the don't care. Well, what's the don't care going to be? Don't care is going to be the 0 number. So don't care is always going to behave as if it's a 0. And 0 multiplied by everything is 0. So it's the 0 number. In multiplication, 0 times everything is 0. So don't care is going to not add any errors, no matter what. So we're done. We have our answer. Let me lower the... Now there's a poltergeist too. Okay. So the don't care is going to behave like the 0 operator. Don't care times a equals a times don't care equals 0. And at this point, we solved two problems. We solved the problem of don't care, and we solved the problem of counting the number of mismatches in every location. Let's look at this example that we had before. When we had a phi, a phi, a phi times b phi b. Okay, so here I didn't need to reverse the pattern because I took a palindrome, so it doesn't really matter. But in general, I would reverse it for the multiplication because, as you saw, it's an artifact of how our second grade teacher did the multiplication. So when we multiply this, we get the green is the multiplication, so b times phi, a times b. Now, we said that phi is 0, so everything times phi gives us a 0. And a times b, because they are different from each other, is going to give us 1. That's how our multiplication works. The second row, because it's a phi times everything, so the second row is a complete 0. It's 0. This is 0 times the entire thing. And the third row is really the same as the first row because it's b times 0 is 0, a times b is 1, and so on to the end. So this is going to be the results of the multiplication. And then when we're adding the columns, we're going to get 1 plus 1, which is 2. Here is 0, 1 plus 1 is 2, and then 0. And indeed, what do we know? We know that if we put b phi b here, we're going to have two mismatches. B and B are going to mismatch. But if we put B phi B here, with the don't cares, there's supposed to be a complete match. And indeed, there's a 0 in the second location. And for the third location, again, there's B phi B. And so it's 2. And the last column, which is this one, B phi B, it's a match. Because the don't cares match. So the result is exactly what we want. And we should be happy now. We should be happy, but we're not really. Because now comes the bad news. The bad news is, what's the time for this thing? N times n. I mean, if you look at what we did, this is n, that's the length of the pattern. This is m, sorry, the length of the text. This is m, it's the length of the pattern. And we multiply them, so what we have is n appearing m times, and then we add. So it's n times m. This is what the operation is. So we worked very hard. We said good things and bad things about our math teachers in elementary school. And we didn't gain anything. Because the naive algorithm is O of nm. So we sit there and we say, oops, what do we do now? It's a common thing. I mean, I remember once someone submitted a paper to a journal, and I was the editor, but I looked at the paper and I saw that it's a very complex algorithm, but there is a known simpler algorithm that does things faster. So I said to the guy, excuse me, why should we care about a complex algorithm when we have something that does it faster in a simpler way? He says, but this is a beautiful algorithm. So I don't know. I mean, we were talking yesterday about the fact that computer scientists are inherently lazy. The idea is that the least amount of work, that's what you want. You want less time, less space, less anything. That's the point. We don't want to put too much effort. So if in time O of nm we can simply solve it, why should we go through all the effort of multiplying it and get the same time? So we're feeling very bad here until we hear the good news. Because then we remember, wow, polynomial multiplication can be done not in time O of nm, but rather in time O of n log m using the fast Fourier transform. So here I'm going to stop, and remember, I told you in the very first day the old Hebrew proverb, Lo Baishan Lamed, which means that he who is shy cannot learn. So I would like to know, especially among the undergraduates, but who has not seen the FFT algorithm in class? Okay, so there are some people who haven't seen it. So let me say a few words about the FFT algorithm, although Professor Mishra and I had some idea about what to do with it, but let me say some things about the FFT algorithm. The FFT algorithm is an algorithm that basically knows how to multiply polynomials, but although, like I showed you, the multiplication that I showed you before we did in time O of nm is really polynomial multiplication where you multiply the coefficients, and then you don't have a carry. So this kind of polynomial multiplication, although the teacher told us how to do it in time O of nm in school, can be, in fact, there is an algorithm that does it in time O of n log m, which, as you know, is faster than O of nm. And that is my third pet peeve, because why didn't they teach us the faster multiplication algorithm in elementary school instead of the slow one? And I'll tell you it's faster, because once when I taught the FFT in undergraduate in the class, I had my TA in the tutorial section. I had him multiply a polynomial of degree 3 by a polynomial of degree 2, and within 45 minutes he managed to do it using the FFT in the tutorial class. So clearly it's faster, right? Okay, now, so it's not faster for human beings, but it is faster. It is faster for a computer. Now, how does this thing work? It's actually a great example of a divide and conquer algorithm, because here is what the FFT is based on. Let's start with, suppose I have a polynomial. Assume polynomial P. So I have some polynomial, and let's say that it's of degree n. And I want to evaluate that polynomial for a particular number. So if the polynomial is of degree n, it's going to take basically O of n squared in order to evaluate it, because if we want to start raising everything to the power of n and then adding all these things, so it's going to take us O of n squared to evaluate that polynomial. However, if you look at the degrees of unity, now the degrees of unity are all the roots of the polynomial x to the n equals 1. So if we look, the roots of unity, sorry. So if we look at the roots of this polynomial, in the real numbers, there are two roots at best. I mean, if n is even, it's 1 and minus 1, and if n is odd, it's just 1. But in the complex field, there are actually n different roots. So there are n complex numbers whose that when you raise them to the power of n, you get 1. Now, pictorially, you can look at it like this. If you draw the complex field as a two-dimensional plane, and if this is 1, this is minus 1, and this is I, and this is minus I. So if you look at this, circle, the unit circle, and you then divide it into n parts. So given n, you divide it into equal vectors where there's n of them here. Each one of them is a root of unity of n, because if you turn it around n times, you're going to go to the 1. So these are the n roots of unity in the complex field. And it turns out, for various not that hard reasons, but we're not going to get into it, that because there is some sort of a symmetry here, anything here has an opposite on the other side. Because of that symmetry, you can actually split this in a divide and conquer fashion. And if you actually if you evaluate the polynomial in all n over 2 roots of unity, you can then use it to evaluate the polynomial in n roots of unity. And what you get is the same recurrence relation, that because it's divide and conquer, the same recurrence relation that you get for merge sort or quick sort, which is T of n is equal to 2 times T of n over 2 plus n, which is O of n log n. So in n log n time, we can evaluate all n roots of unity of a polynomial. Now, why does it help us if we can evaluate all these n roots of unity in n log n time rather than in n squared time? Because, and now we come to multiplying polynomials. If you want to multiply two polynomials, okay, so remember this. It's a black box for people who have not seen it. It's not that hard. It can easily be filled in. But if we take these roots of unity and we want to evaluate a given polynomial p, what is its value in the n roots of unity? Because of the divide and conquer effect, in time n log n, we can get what is the value in the first root of unity, the second, the third, and so on, rather than O of n squared time. Okay, so why does it help us in polynomial multiplication? So all we did here was calculate a polynomial in the roots of unity. So what? Well, the point is this. As we all know, through any 2 points, at least in classical geometry, but through any 2 points, we have one straight line, a unique straight line, through any 2 points. Now, it is also true in general. For any n plus 1 points, there is one degree n polynomial, a unique degree n polynomial that goes through them. So in short, when we have two polynomials, p and q, and we want to multiply them, so we could do it in time O of nm like we saw before. But we could do something else. We could say, evaluate P and Q on nm points. So we choose nm points and we evaluate both P and Q. What is their value? Now, multiply those points. And the third thing is find the unique polynomial through those points. So what are we doing? We're saying I have these two polynomials. Let's evaluate them over a bunch of points. In fact, enough points to get the polynomial of the degree of the multiplication. So we evaluate them on those points. Multiply those points. That will be the result of the... What? Yes, n plus n, yes. Yeah. Correct, n plus n points. Because that's the degree of the multiplication. Yes, we don't want it to be nn. So the n plus m points, which is the degree of the polynomial multiplication. And then, see, I told you about Dieudonné the first day, so it's getting there. So, so we have now the value of the multiplication polynomial in n plus m points. So we know what is its value. Now let's look for the unique polynomial that passes through those n plus m values. That is going to give us the coefficients of that polynomial are the coefficients that we want, are the coefficients of the multiplication polynomial. Now, again, to evaluate it on n plus m points is going to, again, cost us quadratic time. But if there are any old points that we choose. But if we choose the roots of unity, the n plus m roots of unity, at that point we can actually evaluate it, and assuming that they're both the same degree, so we don't need to throw the m in. So we can, in O of n log n, we can evaluate the values of all these points. So in O of n log n times, using the divide and conquer algorithm, we can evaluate both of the polynomials. Then, because we have n 2n or n plus n, because we have 2n points, multiplying them by each other is going to cost us 2n. We multiply one by one, the value of p and the value of q. So it costs us, that's linear time, that's O of n. And now what we need to do is to find what are the coefficients of the polynomial that goes through these results. And it so happens, and that's also the magic of the FFT, that to find those coefficients is really the same thing as finding the finding the roots of unity in the polynomial. It's the Vandermonde matrix, but you change the rows and you multiply the whole thing by 1 over n, and you basically run the same algorithm that you ran for finding the for evaluating the roots of unity, and you get the coefficients. So at this point we're done. So that shows that in time O of n log n, we can multiply two polynomials. Now, for the people who have seen this, this was a reminder. For the people who haven't seen this, it probably is almost useless, what I just said. However, it was only supposed to tell you that it's not, that it's possible, that it's doable, that it's not like impossible. But at this point, even if you did not understand how the FFT works, all you need to know is the following. You have these two polynomials, P and Q. You throw them into the machine called FFT, and in O of n log n time, out on the other side comes the multiplication. Okay, you throw the two of them in, and out comes the product polynomial. Which means that the fact that the teacher told us that to multiply polynomials costs n times n should not be a deterrent to us. In fact, we can do it in n log n. So to get back to our problem, when we have this text in this pattern and we want to find out if the pattern exists in the text. Where does it match with the don't cares? And we also worry about the mismatches. If we're going to do this multiplication, this does not happen. This entire square that you see here, this rectangle, it doesn't happen. This is a black box. Its time is not nm, but it's n log m, and it gives us all the results. So in n log m times, I put this in, and I get the results. And at this point, there's nothing to stop me from going and looking at the results. The zeros are matches. The non-zeros are the number of errors that I have, and the don't care is in there, and everything seems fine. So at this point, we're saying to ourselves, we're now happy. Because, yes, the multiplication helps. It's faster than the naive. So it's not linear time, but it's time n log m. And n log m is close to linear. Log is very little. So that makes us happy. So we had the bad news, then we had the good news. We're now in an emotional roller coaster here, if you notice. Things were bad, things were good, things were bad, things were good. When I moved to Georgia Tech, the first week that I was in Atlanta, the news on the radio started always with the same item for the entire week. And it turned out that that item had been going on for a month. So what happened was they opened the Six Flags over Georgia in Atlanta. Does any of you know what Six Flags is? Yeah? Okay, so Six Flags is this big amusement park where they have the huge roller coasters where they take you up half a mile into the air and then you go down, whoo, like that, and you go through. So this is what Six Flags is. They have all of these torture devices that people pay a lot to go and suffer through. So they opened that Six Flags over Georgia. Now the reason it's called Six Flags is another one is because the original amusement park was actually opened in Texas. And then it was called Six Flags over Texas because the state of Texas in its history had six flags flying over it. The Spanish flag, the French flag, the Confederate flag, the Texas flag, the American flag. So they had six flags flying over it. And the Mexican flag, that's the sixth one. So Six Flags flew over Texas, they called it Six Flags over Texas, but then they opened it in all of America, and they still call it Six Flags. Now, the thing is, they had one of these roller coasters, it was supposed to be so horrible and so horrifying that they claimed that no one could go through even once without queasiness, and certainly not twice without upchucking everything you ate in the last year. So they, in order to prove a point, these guys in Six Flags said, okay, we're going to have a contest. You see this Jeep here? Anyone who can go through this, we're going to have a contest this first day. People who are really hardy and want to be astronauts or something. People who are really hardy can go in, and you'll go through it a couple of times. The one who lasts longest is going to get the Jeep. So a bunch of people showed up, and you know, these Texas guys, they're big beards, and there was a woman also among them, and they all showed up, and they went through the roller coaster, and they all said, give me another one. So they put them again, and again, and again, and again, and the whole day, and by the end of the day, 3 people still remained. And they all said, we want the Jeep. So they said, fine, so we'll go on to the next day. So every morning, these 3 would show up, and they had rules about when they're allowed to stop to go to the bathroom and stop to eat and that sort of thing. And they basically, from morning till night, they ran through the roller coaster in order to weed out the one who cannot last. So that's what the news started with. They said, today is the 27th day when our 3 contestants are still going through the roller coaster in Six Flags. Well, at the end, after about 30-something days, the company decided that it's really not worth it. They bought 2 more Jeeps. They gave it to the 3 of them and said, go away, we don't want to see you. So that was the end of that. But the story only came to illustrate the fact that we are now going through an emotional roller coaster, and we feel dizzy the same way. We were hopeful, and then we said, oh no, and then we were hopeful again, and now we see, okay, n log n, so we're finally done, and we'll get our Jeep and we'll go. No. Because here comes the bad news. So we're down again. Why is the bad news? Okay, remember, and I think it was good that I showed you what I showed you simply because you understood why the FFT is fast. The FFT is fast because I actually drew the complex field. But the thing about the complex field is that it's a algebraically closed field. In other words, there really are n different roots of unity, which isn't the case for the real field, for the field of real numbers. Now, there are also finite fields that are algebraically closed, and in fact, so the FFT could work on some of those fields also. But you need to have an algebraically closed field in order to have the FFT work. Now, what did we do? We said, let's change the multiplication. Let's have a times b equals 0 if they're equal and 1 if they're not. Does that give us an algebraically closed field? It doesn't even give us a field, let alone algebraically closed. So we're still not able to use the FFT, and we're back down to a funny multiplication because it's a funny multiplication, it's not a field. So we have to do the entire thing like in second grade, and we're down to NM again. And after all this, we were so close, and bust again. So now we're saying, okay, forget the Jeep, let's just go home. We're so sad. But there is still light at the end of the tunnel. Okay, so does everyone understand now why we're so sad? Because we thought that we have such a great solution to the don't care problem. And on the side, also solve the mismatch problem. We can also count the mismatches. We thought that we had all of this, and then only to have it snatched from in front of our eyes just because of a simple thing like that we don't have an algebraically closed field. So this is why we're in a deep, deep funk. But being computer scientists, we never give up. And in computer science, what do? If you can't solve a problem, you reduce to a problem that you can solve. This is the kind of thing we do. So in Israel, we have a story, and it's an educational one, about making tea. So they ask a mathematician, and they say, listen, you're in this room. Let me see that I have it all straight. Okay. You're in this room, and you have a kettle and water in this room, and you have fire in the other room, and you're supposed to make tea. So how do you do that? So the mathematician says, okay, fine, I take the water in the kettle, I go to the other room, I put it on the fire, wait for the water to boil, and then I pour it into my glass and I make tea. Then they ask a computer scientist, okay, same question. Says, I'll give you an algorithm. Step number 1, put the water in the kettle. Step number 2, take the kettle to the other room. Step number 3, put it on the fire. Step number 4, wait for it to boil. Step number 5, pour the water into the cup with the tea bag, and you're done. Okay. So now they say, all right, harder question, mathematician. The water and the kettle and the fire are here in this room. How do you solve it? Says, fine. I take the water, I put it in the kettle, I put the kettle on the fire, I wait for it to boil, and when it boils, I pour it into the cup and with the tea bag, and I have my tea. Okay, so they ask the computer scientist. Same question, what do you do? He says, okay, I'll give you an algorithm. Step number 1, take the water and the kettle, put it in the other room, and that problem we already solved. So this is what we do. We want to simplify things and use what we know. So he reduced it. He reduced it to a problem that he knows how to solve. So if we know how to solve, if we know how to do multiplication in an algebraically closed field, then let's see how we can use our funny multiplication and reduce it to a real multiplication. So that's the promising news. And fortunately, this is the end of the roller coaster, because at this point we have our solution. Once you get to the computer scientist taking the tea and the water to the other room, you know that you're done. Everything's good. So let's look at what's happening. Our multiplication, okay, let's first of all take our alphabet to be binary. And that's a trick that is a common trick in pattern matching. Whenever there's a hard problem, one of the simple things that people like to do is say, okay, let's assume the simplest alphabet we can have, a binary alphabet, and see if we can solve it there. And if we can solve it, we'll generalize. And if we can't solve it in binary, well, we have a problem. So, assuming that we have a binary alphabet, the way that our multiplication works is the following. If we have a text in the pattern, and if the pattern is 0, and we multiply it by a 0 in the text, we get a 0. But if we multiply a 0 by a 1, we get a 1, because they're different. So what we said was that whenever the symbol is the same, we get a 0. So 0 times 0 and 1 times 1 both get 0. And when the symbols are different, our multiplication, our funny multiplication, gives us a 1. So this is how the multiplication table looks for our alphabet. On the other hand, in the complex field, which is where we do know how to multiply fast polynomials, and the fact that we're multiplying zeros and ones doesn't matter, because the coefficient can be a 0, the coefficient can be a 1. Those are also complex numbers. But limiting ourselves to zeros and ones, this is the multiplication table, because 0 times everything is 0, and only 1 times 1 is 1. And here, looking at these multiplication tables, you can see the inherent problem that you have with why it's not going to work. If this multiplication works, this one doesn't. It doesn't even look the same. However, and this is what I mean by moving things to the other room. So, yeah, it's not the same, but what happens if we start moving things to the other room? So let's see how we're moving. So if we exchange the rows in our multiplication table, so we exchange them, we're almost there. So see our multiplication table. Do I have it somewhere? Okay. Where was our multiplication table? Okay, so yeah. So this was our multiplication table, and this is the table that we want to get to. So if we exchange these rows, we're almost there, because we get the 1 here, so we get 0, 1. The bottom row is the same, but on top, we get 0, 0. Instead of 0, 0, we get 1, 0. Okay, so let's see the picture here again. So that was the first thing we do. Now, if we exchange the columns, we're also going to, I don't know what I meant by these pictures anyway. If we exchange the columns, we're also almost there. Let's go back here because that makes sense. So if we exchange our columns, we're also almost there, because if we exchange the columns, again, we end up with having a 1 here and a 0 here, and the 1 here and a 0 there. So both if we exchange the rows or if we exchange the columns, we're almost at the multiplication of the complex field. Actually, now I understand what I meant. I managed to confuse myself here. Okay, so it's true, but symmetrically true. So what I did here, this is our multiplication. What I did here is exchange the rows and the columns, not of our multiplication, but of the complex multiplication. So if we exchange the rows of the multiplication table, we get this, which is almost the same as us. It's just that the one is missing here. And if we exchange the columns of the complex field multiplication, we get that, which again is almost the same as our stuff. But look at what's interesting here. If you take the rows that were exchanged and the columns that were exchanged, and if you add these two matrices, then you get exactly our matrix. Okay, so take the multiplication matrix of the complex field, exchange the rows. Take the multiplication matrix, exchange the columns, and then add them, and what you're getting is exactly our multiplication. What does it mean? It means that if somehow we can simulate an exchange of the rows and simulate an exchange of the columns and then add the result, we're going to get our multiplication just by doing two FFTs, which is 2 times n log m. It's still n log m. So by doing two FFTs and then an addition, which is O of n, we're going to be able to actually get our multiplication. Now, what does it mean, simulate an exchange of columns or an exchange of rows? I mean, what does it mean to exchange the row? It means that every one that was in the pattern, in the text. So to exchange the row means that every one in the text we're going to change into a 0. And every 0 in the text we're going to change into a 1 and do a multiplication. In effect, it means that we exchange the rows. And to exchange the columns means that every 1 in the pattern we turn to a 0 and every 0 into a 1. And in effect, what it means is that we exchange the columns. Because when you multiply a 0, you're going to get the result of multiplying a 1. So it's like you change the column. So what does it mean? So now we put all of these together, and we get our result that if you take the text and you exchange every 0 by a 1 and every 1 by a 0 and multiply it by the pattern and add it to the text times the pattern where you exchange every 1 to a 0 and every 0 to a 1, these are regular multiplications. These are multiplications that you use FFTs. But the result of this is going to be the result of the funny multiplication, of our funny multiplication. That's what the result is going to be. And so, finally, we breathe a sigh of relief because in time, O of n log m, we actually did manage to do the matching with the don't cares. And in fact, with the counting of the errors as well. But of course for a binary alphabet. So let's look at this example and see exactly how it worked. So the old test that we had, A phi, A phi, A phi, and the pattern B phi B. Because we're not talking now about A's and B's, but about zeros and ones, since we're going to have to multiply things. So let's say that the A is 1 and the B is 0. So the text is 1 phi, 1 phi, 1 phi. The pattern is 0 phi, 0. Now, again, the phi is always going to be 0 in all the multiplications because we never want the phi to generate a mismatch. So if the phi is a 0, whatever is in front of him is always going to give us a 0 in the multiplication. So what do we get by the by the complement of t times the reverse of p? Okay, so p was 0, 0, 0. T reverse is everything is 0, so the result is one big fat 0. That's the result of the first multiplication. And this result we get in time n log m. Now, the other multiplication is the one where we get the t, which is 1 phi, 1 phi, 1 phi. We multiply it by the reverse of the complement of p, which since p was 0, phi 0, it's now going to be 1 phi 1. The phi is always 0, okay, so that is always the case. So when we multiply that, this is the result that we get, 2, 0, 2, 0. And when we add the two of them, we get 2, 0, 2, 0, which we know that was the original result. So again, the reason that this worked is because we somehow reduced our funny multiplication to a multiplication that we know how to do fast, and that was the complex field multiplication. So here we are, and we solve the problem for an alphabet of 2. Now, for people who feel that they're a little bit lost, don't lose hope yet, because we're going to simplify things a bit as we move along, and I think that it's going to be even clearer. So what you need to know now in order to continue is not to dwell with a deep sadness on what you didn't understand, but in fact to look with happiness on what you do understand. And what you do understand is the following. You understand that if I do know how to make a multiplication, then I can in fact solve the don't care problem. And you know also that there are ways of doing fast multiplication, and all we need to still, and we're going to see an even easier way, is how to reduce our multiplication to the multiplication that we know how to do fast in order to get the final solution. Now, in addition to that, you're also discouraged because we only did this for a binary alphabet. Yes, that is a discouraging point, but no sooner do we solve one problem, there's one underneath that's waiting to be solved. So we're going to solve that one as well. The phis we don't switch to ones because phi is a don't care. Now, what does it mean whenever you have a 1? If you multiply it by a 1, you're going to get a 1 in the result. Now, in our case, every 1 in the result is bad because it means a mismatch. The 1 means a mismatch. A times B equals 1 when A is not equal to B. But the phi never mismatches anyone. So the phi never gets changed to anything because it's a 0. It multiplied by anything gives you a 0. It never generates a mistake. Yes, that's how we treat it. The 0 is a 0. The complex multiplication needs to account for the elements that don't match each other. So a real 0, a 0 in the alphabet, times a 1 needs to be 1. But of course it's not going to be. That's why you change the 0 to a 1. And at that point when you multiply them, you are going to get a 1. And the real 0 in the text multiplied by a 1 in the pattern should also generate an error. And it wouldn't in a regular multiplication. But that's what you get when you change it to a 1. So 1 times 1 is going to give you and the point is that they never coincide. It's either 0 against 1 or 1 against 0. So by changing, you never double count a mismatch. So exactly the mismatches get counted. 0 in the text times 1 in the pattern, 1 in the text times 0 in the pattern, and don't cares are always zeros. Because of the way that we changed it, that's how it, so doing those multiplications and adding gives you exactly what you want. Okay, so now comes the question, what about larger alphabets? All right, we have said in the previous days that, it's a funny thing because, like we said 3 days ago, usually when I teach the class, and I said we have said, it was like 5 weeks ago. So it gives a different, the relativity of time. So we have said that we may even be talking about infinite alphabets. It could be that our alphabet is numbers, and so it's infinite because you have an infinite amount of numbers. So if we're talking about an infinite alphabet, what are we going to do then? How do we then do our reduction to the multiplication? Okay, so the first observation we're going to make is that we are never talking about an infinite alphabet, because our alphabet size is always bounded by small sigma, which is the minimum of n plus 1 and the size of the alphabet. So the alphabet may be 10 to the 100, or it may be even infinite, but the size that we care about is the minimum of n plus 1 and that. So if the alphabet was 2, the minimum is going to be 2. If the alphabet was infinity, the minimum is going to be n plus 1. Why is that? Because the fact of the matter is that you don't care how many symbols there are in the text. You only care how many symbols there are in the pattern. When you're trying to match a pattern to a text with don't cares and count errors and whatever, okay? So anything that matches a pattern symbol in the text is a match, and anything that doesn't match a pattern symbol is a mismatch. So all these infinite numbers that are not in the pattern, exchange all of them by the number 613, assuming it's not in the pattern. So you now have the text and the pattern only having sigma n plus 1 symbols. So the first thing to notice is that relax. We're not talking about infinite alphabets. Infinity is always a big thing, and so we're not talking about that. One of the epiphanies that I had, when I found out that there's an infinite number of different infinities, to me that was amazing. I wasn't, first of all, I understood why Cantor went crazy at some point, but because the mind can't take this concept. But it's beautiful. All right, but nevertheless, we don't like to deal with infinities. Not many and not one. So we don't have infinities. We just have this sigma, which is n plus 1 in sigma. Why? Because of what I said, and it's written here. If pi is all the x's in sigma that are also in p, and alpha is not in pi, then every text location that is either in pi or don't care, or we put alpha in it. So therefore, our alphabet is of size n plus 1, and then we have the don't care. All right. And obviously, to do all this, we can easily do it in time O of n log m, because every text, run through the text, every text symbol. You do a binary search on the pattern, and you can, on the pattern symbols, and you can see if it's there or not. So in n log m, you can do it. And at this point, we don't worry about paying n log m because the FFT is going to be n log m anyway. So we're not really wasting too much time. Okay, but now that we know that that's the case, let's encode every alphabet symbol in binary notation. So this is something else that as computer scientists we love, is binary. So you have an alphabet. The alphabet is of size sigma, which is at most n plus 1. So, and you want to write it in base 2 in binary notation. How many bits are you going to need? Log sigma. Okay? So we encode every alphabet symbol in binary notation. We're going to need log sigma bits. Now we're also going to encode the phi by log sigma bits. Now what am I doing now? What I want to do is actually convert a general alphabet to a binary alphabet. And so what I'm going to do is say, all right, let's write the general alphabet in binary. So now I'm going to have this text and the pattern as zeros and ones. And so if there's a match between two letters, two symbols, there's going to be a match between their binary notations as well. And therefore, if I find a match in the binary, I'm going to find a match in the original. And that's good. But if I'm going to find a match with don't cares, I cannot leave the don't cares as a single bit because everything else became log sigma bits. So the don't care itself has to be blown up to log sigma bits as well. And at this point, I'm going to do a binary multiplication, which we know how to do. And anything that matches with the don't cares is going to be a match, even for the infinite alphabet. So that's the general idea. So we have the pattern matching with don't cares, and we can solve it in this time. Now I'm going to, let's talk about this a minute, how we get that time. Okay, so suppose my alphabet was A, B, C, D. So if it's A, B, C, D, and I want to convert the whole thing to binary, the A, I can write it 0, 0, the B is 0, 1, the C is 1, 0, and the D is 1, 1. Okay, so I can convert it just by log of 4 here is 2. So by 2 bits, I can encode this alphabet. So if my text was A, B, A, C, D, then the new text is going to be 0, 0, 0, 0, 0, 1. Phi is phi, okay? Because, again, it needs to match a symbol, and every symbol now became 2. So there's phi. A is again 0, 0, C is 1, 0, and D is 1, 1. So that's what my text is going to be now. And now my text is actually binary. Now let's assume that my pattern was A phi C. Okay, so let's assume that that was my pattern. Now, in this text, the pattern would match here, and the pattern would also match here. So these are the two places where the pattern would match in the original text. Now, the pattern itself is going to become 0, 0, phi, 1, 0. Now, this 0, 0, phi, 1, 0 is going to match here, 0, 0, phi, 1, 0. And it's also going to match here, 0, 0, phi, 1, 0. Because all the A's that matched, their binary representation is also going to match. All the B's that match the C's. I mean, all the letters that match, their binary representations are going to match. And anything that matched the phi, its binary representation is now bigger, but the phi is also bigger. So it's going to match the phi. Now, there's a danger. The danger is that we may find something that shifts and matches. Because, who knows? I don't know, even maybe in this example. I'm not that much of a computer that I can look at the example and say, okay, here it is. But it could be that a shift would match, but it doesn't mean anything as far as the original one does, right? Because in the original, suppose that these are the letters. And so all these matches are indeed going to be caught by the matching strings. But it could be that this string would also match with the don't cares. And it's meaningless as far as we're concerned because it's in the middle of a letter. But that's okay because we can look at our results and do it mod log sigma. So any result that is not 0 mod log sigma, we're going to ignore. And anything that is, we're going to divide by log sigma, and we get the index in the original one. So we're going to be okay. Is everyone all right with that observation? Okay. So this is what we're going to do. And we know, now, why are we doing all of that? Because we know how to multiply zeros and ones in our funny multiplication using FFT. So we're basically going to take the text, this new text. Okay, so this was the old text. Let's say that P prime and T prime is the new text and pattern. So we're going to take T prime times PR plus T times P prime R times the complement of P prime R. We're going to take that. We'll take the results, divide the indices by log sigma, and all the results that we get, all the indices that are 0, all the 0 indices that we get, that we divided by log sigma, and we got a whole number, that is going to be our solution. So the only thing that we need to find out is how long does it take us to multiply this. Now, we know that the time it takes us to multiply is n log m, but now the n and the m changed because we added this log sigma. Okay, so we're almost there, but in order to see why we got this as opposed to n log m, so let's plug it into the formula. So what we have is that the length of T prime is n log sigma. And the length of P prime is m log sigma. So call this big N, call this big M. And we know that we can get the result that we want in time O of big N log big M. So all this we know. Now let's plug back the n and the m. So this is equal to O big O of n log sigma times log of m log sigma. Okay? So this is equal to O of n log sigma times log m plus n log sigma times log sigma. And this is just because of logs. That also the teacher taught us in elementary school. So because log sigma is smaller than log sigma, and log sigma is smaller than log m, so this actually gets dominated by this, and we get n log sigma log m. So that's the time that we get for a general alphabet. Any alphabet, even an infinite alphabet, we can do pattern matching with don't cares in time n log m log sigma. So at this point, we could be happy, and we could say, all right, we solved what we wanted to, except for one thing, we're insatiable. And on the way to solving it, we said, well, the multiplication also counts mismatch. Does it count my mismatches? The sad answer is no. It solves the don't care problem. Okay, that we saw. So it solves the don't care. But it does not solve the mismatch problem. And the reason it doesn't, you can see in the example up here. So suppose that log sigma was equal to 3. And this was the text. and this is the pattern, in some particular point. When you do the multiplication, what you get here is, because the pattern is not equal to the text, in 3 locations here, plus 3 locations here, plus 3 locations here, you're going to get 9-bit errors. And these 9-bit errors represent 3 real errors, 3 errors in our alphabet. On the other hand, the same 3 errors in our alphabet, if this was the text and the pattern is still the same, here it would give us only 1-bit error here, 1 here, and 1 here, so we only get 3-bit errors. Which means there could be cases where the original alphabets gave us X amount of errors. Our binary alphabets, the number of errors it's going to give us is between X and X times log sigma. Because it could be that every error generated log sigma errors. And it could be that it must have generated at least 1. It could have generated log sigma, and it could have generated anything in between. So we do not have an exact measure of how many errors we have. And so, who spoke about errors before? I mean, but since now we have a tool that gives us errors, so now all of a sudden we are greedy and we say, well, we want to count the errors as well. So let's see what is the solution here. Okay, so for each, again, we're going to use the old, true, and time-tested computer science philosophy of reducing the problem. We know that we know how to multiply, how to use the FFT for binary alphabets. In other words, not only that, let me even say what is the FFT property that we know how to do in time n log m that is really crucial to us and that we're going to now exploit to the fullest. So the property is the following. When you have a binary number, zeros and ones, and you multiply it by zeros and ones, what really happens with the multiplication? The multiplication does the following. It takes the number of the pattern, the smaller number of zeros and ones, juxtaposes them against the first position of the text, and does a dot product. Dot product meaning it multiplies 1 by 1 and adds the result. What does it mean? It means that every clash of a 1 in the pattern with a 1 in the text is going to be counted. And that's what's important. So what we're going to do is the following. We have a pattern of zeros and ones. We have a text of zeros and ones. What we know how to do is shift the pattern across the entire text, and for every shift, we can do the dot product. In other words, we can count the number of clashes of ones and ones. And all that we know how to do in time n log m. This is exactly what the FFT tells us. Okay, so now again, for people who still are confused with the FFT, so assume that your black box is the following. Because this is everything. This is it. Assume that your black box is given a text T of zeros and ones, T over 0, 1, and a pattern P over 0, 1. Let's say this is the pattern. We can, for every shift, count the number of ones that clash And all this in time O of n log n. So in this case, we're going to put this here. We shift, no clashes, so it's going to be a 0. The next shift, we're going to put the 1, 0, 1, 1. And so there's a clash here and a clash, there's a 1 clashes with a 1. Sorry, let's go back again. I confused myself again. 1, 0, 1, 1. We're counting how many 1s clashed against each other. So 1 times 1 plus 1 times 1 plus 1 times 1 is 3. Then when we move again, we put it 1, 0, 1, 1. 0 times 1, 0 times 1, 1 times 1, 1 times 0. So here there's only 1. And if we shift it again, 1, 0, 1, 1, 1 times 1 and 1 times 1, so we're going to get 2. And you go on through the entire text and do that. So that's what the FFT, in fact, does for you. You multiply it and you add the 1s. And that you know how to do in time O of n log n. So now that this is the big hammer that you have, here's how you solve it. Take every symbol in the pattern. So pi was the pattern alphabet. We take every symbol A in the pattern alphabet. And count for each, and count separately for each pattern symbol how many text locations mismatch that A. Okay, so let's fix A. Fix a letter in the pattern. The pattern now has 4 letters, not 2. It's a 4-letter pattern. So take the first letter, let's say it's A. Let's count for every shift how many A's in the text mismatched, not how many A's in the text, how many letters in the text mismatched this A. And then let's count how many letters in the text for every shift mismatch a B. And then let's count how many letters in the text mismatch a C. And then let's count how many letters in the text mismatch a D. Add them all up together and we get all the mismatches. Because we counted all the mismatches of A, all the mismatches of B, all the mismatches of C, and all the mismatches of D. Okay? Now, how do I count how many letters in the text mismatch the pattern? Now, I'm going to shut up because I want you to think a minute. Assume that you have this. In time n log m, you know how to count clashes of 1s. All through the... Can you use this tool, counting the clashes of 1s, in order to count how many letters in the text clash with A in the pattern? As soon as one of you sees the answer, ding. But it's going to be like the minimum of sigma and whatever. So either you ding first or a minute passes and then I will ding. But so I'll give you about a minute. You want to repeat the question? Okay. So here's what I want to do. I want to take a symbol in the pattern, A. Now, A appears many times in the pattern, right? The pattern may be ABC, AA, CC, BB, ABC, ADD. So A may appear many times in the pattern. What I want to do is find out for each location in the text, if I juxtapose the pattern in that location in the text, I want to find out how many A's in the pattern mismatch the text. In front of them, in the text, is not an A. If it's an A, I don't count it. It's not a mismatch. But if it's not an A, it's a mismatch, and I want to count it. So I want to know this for all locations in the text, and I want to know it in time O of n log n. Now, the tool that you have is the following. In time O of n log m, what you know how to do is this. If you get a binary string of 0s and 1s, and a binary string of 0s and 1s is the text, for every shift, you can count exactly the number of ones in the pattern that have a 1 in matching them in the text. And that you know how to do in time n log m. Now can you use that to solve the problem with the letter A? No, nothing. Maybe I'll encode, but I'm saying this is what I know how to do. Yes. And in the text, what do you do? Almost, because what you're going to do then is count every A that matches. And I want to count every A that mismatches. So the opposite. Excellent. So here is the answer that was suggested. Here, write your name down and I want to go and read it. Yeah, people know here that when you tell me a name, it's useless. But when I read it, it makes some sort of a sense. Darshil. Okay, so Darshil suggests the following. He says, what do I know how to do? I know how to count clashes of ones in all shifts. What I want to do is count clashes of A in the pattern and non-A in the text. So all I need to do now is construct a pattern that has 1 everywhere where there was an A and 0 everywhere where there wasn't an A in the pattern. Construct a text that has the opposite. 1 everywhere where there wasn't an A in the text and 0 everywhere there was an A. And boom, multiply it. In time n log m, I'm going to have for every position the number of clashes of ones. But the number of clashes of ones is exactly what I wanted. These are A's clashing with non-A's. All right, so let's formalize this. So the characteristic function chi A of B. So Americans can't say chi because there isn't a ch in the English alphabet. In Greek, of course, chi was chi. So that's why in the United States they call this chi, but it's a chi. Okay, that's the Greek letter chi. Now, and they also say characteristic function, where it's ch, because they can't say characteristic function. That's why it's a chi, because it's a characteristic function. But okay, fine. Since I'm speaking English, but I'm writing Greek, then I'm going to say chi and say characteristic. So the characteristic function chi A of B is going to give us 1 if A is equal to B and 0 if A is not equal to B. That's the definition of a characteristic function, and that's how it works on a symbol. And we're going to say that the characteristic function on a string is just a concatenation of the characteristic functions on the symbol. And the characteristic function of the complement of a letter is the concatenation of the complement of the characteristic functions on the symbols. So our algorithm for counting all mismatches is going to be the following algorithm, and here it is. And we're going to see an example also, so you can all relax. So we're going to do the following. For every A in the alphabet of the pattern, we're going to take the characteristic function of the complement of A. In other words, everybody who is not A in the text becomes a 1, and everyone who is an A in the text becomes a 0. And we multiply it by the characteristic function of the pattern reverse. We multiply that, we put it into VA. We do that for every A, and then we add all the VAs into V, and that's the end of our algorithm, and we counted our mismatches. Now, because we counted the mismatches letter by letter. We counted all the mismatches of A, all the mismatches of B, all the mismatches of C, and since those are all the letters in the pattern, when we add them up, we get all the mismatches all together. So that's our algorithm. And the time for the algorithm, obviously, because each one of these multiplications is a fast Fourier transform. So each one is n log m. So n log m times pi, because pi is the size of our alphabet. If we're dealing with the genome, for example, it's going to be over 4 times n log m, and we can count all the mismatches. let's see an example, and after the example we can probably, at that point everyone will have earned a well-deserved break. And yeah, question? This actually, at this point, I just counted the errors, but everything would work for don't cares. Just throw in a 0 every time there's a don't care, and it's not going to add any, mismatch. So don't cares fit in here without a problem because we're doing complex multiplication. 0 is 0. So whenever there's a don't care, put in a 0. Yes, the characteristic function. The characteristic of A on don't care is always a 0, no matter what. Okay, so here's the example. Let's look at the text. We're making it, and again, I did away now with the don't cares because, like I said, that's why add more noise. So let's just count errors. If this is the text, A, B, C, C, and this is the pattern A, B, C, let's see the number of errors that we have. A, B, and A, B, C, the number of errors here is 2 because the A matches, but these two are errors. Now, if we shift one, A, B, C, there's 0 errors because everything matches. There are no mismatches here. And then if we shift one more time, A, B, C, we get 2 again because the A mismatches the B and the B mismatches the C. All right, so this is the what we want to see at the end of this experiment. And our alphabet is ABC. So we have a 3-letter alphabet. So what does our algorithm say? Our algorithm say, take all the A's in the pattern and count how many mismatches are generated by these A's in every location. So in other words, for the first location, A in the pattern doesn't have a mismatch. For the second location, it doesn't have a mismatch. In the third location, A is going to have a mismatch. So this is kind of what we're expecting to be. So we'll count all the mismatches that the A generates. Then we'll count all the mismatches that the B generates. So for the first location, B generates a mismatch. For the second, it doesn't. And for the third, it does. And then the C generates a mismatch for the first location, not for the second, not for the third. If we add all those up, we're going to get the numbers that we wanted. Because first we count the number of A's that mismatch. Here it's 1. Then here it's 0. Here it's 1. Then we count the number of B's. And so here it's 1 also. Sorry, here it's a 0. B is 1 here, and none here, and 1 here. So this already gives us the 2 errors here. And then the C generates an error here. So add it up and we get a 2. No error here and no error here. So all we do is we actually count them, not by putting the ABC everywhere and counting, but rather count the A's, count the B's, count the C's. And we count it by doing the FFT. And the FFT is the following. So ABC, we want to count all the clashes of A's and A's. So of A's and not A's, I mean. So what we want is everywhere in the text where there's an A, there's going to be a 0 because we don't want to count such a clash. So if it's a A in the text, I don't want to count the clash with an A. So we'll put a 0, but the BCC are going to be 1s because a B that sees an A in front of it wants to count the clash. So it's going to be a 1. Now, in the pattern, it's going to be 1, 0, 0, but obviously we reverse it because of the because I want to show it through the multiplication. And so the multiplication of this thing gives us that 1, 1, 1, 0, 0, and all of these. You add them all up and you get a 1 here. What does that mean? It means that as far as the A is concerned, the third location, in the third location, which is this one, we have an A clashing with a B. So we have an A clashing with a B here. That's this one that we get. In all the other locations, the A didn't clash because there was an A in front of it. So this is the one that we got here in this multiplication. So now we know that is the number of errors that the A's generated, the number of mismatches. Now we're going to the B's. So the B is the same thing. There's only one B in the pattern, and so in the text. So that B should not clash with anybody. That's a 0. And everybody else is going to clash if it sees a B in front of it. In the pattern, there is a B here in the middle. So that's the pattern. In this case, the reverse is the same. When we multiply it, we get this, which is 1, 0, 1. Again, what does it mean? This is the first location. And what it means in the first location is that the B, in fact, saw an A. We multiplied here. You put it here, 0, 1, 0. So 0 times 1, 0 times 0 is 0. But the 1 times 1 added, that was this 1. And this is this clash in the first location. In the second location, the B had a B in front of it. So everything was a 0. And in the third location, there was a B and a C. So this 1 times the C, 1 times 1, is what we got here in the third one. So we get 1, 0, 1. These are the clashes of the B's. And finally, we go to the C's. And everything that's not A, that's not C in the text are these. And the last two elements of the text are C. The pattern was ABC, so 0, 0, 1. Reversed is 1, 0, 0. We'll multiply this and we get that. Because, in fact, this is the C. 0, 0, 1. That's A, that's B. We don't count the A's and the B's. But the C in the pattern clashes with a non-C in the text, and that's this one. So we get it. When we add these three vectors, we get 2, 0, 2, which is exactly the number of errors that we wanted that you saw up here. 2, 0, 2. And the time that we spent was 3 convolutions, so it's 3 times n log n. So for bounded, and I'm going to exactly now wrap this up. We'll go to the break and then come back with even more exciting stuff. So for bounded alphabets, for example in biology, where this is what you have on your RNA, our time is O of n log m. For unbounded alphabets, and this is the sad thing, our time comes out to m because the sigma for unbounded alphabet is going to be m plus 1, which is O of m. So you do m multiplications. Now, mn log m is worse than nm. I mean, you're really, really suffering. So, so you're going to go now to the break with this heavy heart saying, what are we going to do for counting mismatches of infinite alphabets? But let me tell you, let not the tea sour and curdle in your stomach. You can rest assured that there is going to be a solution, which will be presented right as soon as you come back. So go and enjoy your tea and come back happy to look for the solution to this quandary. So remember what our task is now. Where are we? We managed to prove that that no matter what the alphabet is, fairly efficiently, we can do pattern matching with don't cares, even though don't cares are not transitive. And that's by using the convolutions. Now, we showed that for infinite alphabets, the time is n log m log sigma. The truth is, and I didn't bother going into these details here, but there was a paper written about 10 years ago that showed how to do it in time n log m without the log sigma also, by Clifford and Clifford. So, but the bottom line is log m log sigma and log m without the log sigma, they're both small enough and close enough to linear that, that as far as the don't cares, we are fairly satisfied. We also showed that for a bounded, finite, fixed alphabets, especially small alphabets, like in the DNA, but in fact, even the written alphabet, if you have 20-something letters, it's not a big deal. Or ASCII, or gray levels, or colors, these are all fixed alphabets. From a theoretical point of view, we're talking about, for all intents and purposes, something finite, something small, and therefore, if you're talking about huge texts and patterns, you will be talking about small number of FFTs. Now, let me also say something else about the FFT. The FFT is actually very prevalent. All our computers, I mean, they all have hardware that knows how to do FFT very fast, and in fact, even in parallel. So the FFT can be done fast, and we have hardware that does it. So anybody who wants to do pattern matching and count mismatches or things like that, and do large FFTs, there's hardware that does it. There's even software that does it. You can go on the internet and get free software. There are many free packages that you get that do the FFT fast, the fast multiplication, and you can do that. And I even had once a master student that wanted to find out when does doing the FFT become effective? When should you do it? For how big patterns in text? Because obviously n times m for small n's and small m's is not that expensive, and why not do it that way if you want to count mismatches or do don't care? And she found out that you don't need to talk about huge millions of texts in the length of millions. Even texts in the length of a few hundreds, already doing the FFT becomes more efficient than doing it by the brute force method. So this is actually not just theoretical. What we saw now, it's in fact useful. You can do things faster this way. In reality, in practice, it's faster. However, we were still stymied by the fact that if we want to count mismatches, and if we were looking at unbounded alphabets, or even alphabets that are roughly the size of the pattern, we are doing worse, even theoretically, let alone practically, than the naive algorithm. So the question is, how can we solve it? So we're going to now look at the technique called the two glass balls, and that's why I called it two glass balls and a tower. And the technique is the following. So we're going to start again with a game. Now this game is actually a question that many high-tech companies in Israel used to ask people that they interviewed because they felt that that shows who's a good programmer and who understands computer science. Today the good companies don't ask it because they know that everybody knows the answer. But it used to be years back that they used to ask it. And you probably have seen it also, but let's go through it simply because because what I'm interested in is what we can learn from it, not so much the question itself. So what's the game? The game is this. Some chemistry professor here figured out some glass that is really unbreakable. And he made a ball like that, and he says, wow, I think that this is a very sturdy glass. It really doesn't break. But I want to know, when does it break? So there's a very tall building in town. I don't know how tall the buildings we have here in Gandhinagar are, but suppose that there is a very tall building, and so he wants to know what is the floor K such that if you drop it from that floor, the ball is going to break, but if you drop it from floor K minus 1, it's still okay. So that's the question. I want to know how far up it's not going to break, up to K minus 1, and what's the first K where the ball breaks. So that's the question. So pictorially, you throw it from K minus 1 and everything is good. You throw it from K and kablooey. So the ball shatters to smithereens and it's no good. So that's what we need to know. Okay, so now, how does he test it? So obviously, he's going to take the ball. He's going to grab his graduate student and say to him, here, take this ball and come back and tell me what is the K for which the ball breaks and K minus 1 doesn't break. So he gave that ball to the graduate student. The graduate student obviously has to do it. So we were talking about the fact that already 3,500 years ago, Judaism said that slavery isn't allowed. But graduate students are still slaves to this very day. So if the professor says you have to do it, then he has to do it. So he, how is he going to do it though? What's his algorithm? He has no choice but to do a sequential search, because anything that it does, if the ball breaks at some point and he doesn't know that it didn't break for anything below, he doesn't have the answer. So he has no choice. He's going to go to the first floor, drop the ball. Then if it didn't break, he's going to the second floor. And if it didn't break, he's going to go to the third. And then to the fourth, and it broke, so he says, good, I have my answer. 1, 2, 3 didn't break, and 4 broke. And the time, if we want to do it, if we want to compute this time, in computer science terms, the time is O of n as every sequential search. So it's linear time, but it's O of n. You would like to do this better than that. Okay. So actually, yesterday I did a sequential search on the buildings here, because somehow I missed Professor Mishra, and so I walked here. Now walking here is easy because you see the target, so you just walk to it. But then once I got here and I saw all the buildings, I remembered we were in room 202, but I didn't know which building. So I said, let's do sequential search. So I went to building 1202, I saw it wasn't that. Then I went to building 2. Then I said, this is stupid to do sequential search. We should do a random access here. So I took out my cell phone, and I looked at the site, and it said that it's in building 6206. So then I did random access, I came straight to building 6. So sequential search, as we know, is slow, and especially where every time it meant climbing up, going to the room, no, it's not the one, go down, go to the next room. This is not, it's not right. So we don't want to do sequential search. So here's another strategy. It turns out, fortuitously, that this glass not only is it shatterproof, but it's also very cheap. So the professor made like a whole box of them, and he took this huge box and gave it to the graduate student and told him, here, tell me where the ball breaks. So at that point, now the grad student is very happy, because he says, I have all these balls, I can do a binary search. So he says, good, I'll drop it from the middle, and if it broke, then I know already that it can't be in any of these, so I already eliminated half of my trials. So I'll go halfway down between the middle and the beginning, and I drop it, and the ball didn't break, so fine. But I eliminated this, now I know that I'm in this. And you keep going, and in O of log n experiments, you're going to find exactly the k that you want. Okay, so far there's nothing new. So far there's nothing new. But now comes the new question. So the professor comes and says to him, listen, I don't have an infinite amount of balls to give you, so you can't do a binary search. But also, I feel it's a little stingy to give you only one ball. So here, have 2. Go and tell me where the glass breaks. So now, what's the strategy that the student can do? So this is the question that those high-tech companies used to ask. So if any of you did not hear this question before and you want to have a crack at the answer, you can try it. Suppose that I'm interviewing you for a job. So what is the student going to do when he has 2 balls? Well, you can't do binary search, obviously, because, well, you can, I guess. You can start in the middle. And then if it breaks, you at least save yourself half. But at that point, you're going to need to go sequential, either here or on the top. So yes, you saved half of n. Yes. So you saved half of n, but it's still O of n work. So asymptotically, you're still working O of n. And you would want to somehow asymptotically do a little bit better. But again, once a ball breaks, it breaks. So you're in trouble. Yeah? So what are you saying? You take the ball and... two, 3, 2, 3, 2, 3. Okay. But again, the worst case, wouldn't that be O of n? All right. But here is what the student can do that actually gives you asymptotically a better solution. Divide the building into blocks of square root of n floors. How many such blocks there are? Square root of n, because root n times root n is n. So we have square root of n such blocks. Now, what you're going to do is the following. Use the first ball to find what is the block that is right above the block that the ball breaks. So throw the ball from the top of the first block, and it didn't break, so you know the first block is good. Throw it from the second block, you know that it's good. Throw it third, you know it's good. Fourth, oops, it broke. All right, so now I lost a ball, but I do know that all of this is good. I do know that all of this is bad. How many floors do I still need to test in order to make sure? Square root of n. So again, you're going to do this sequentially. So you throw it here, and it breaks. Asymptotically, how many experiments did you make? Square root of n. And square root of n is clearly better than m. It's not better than log m, but it's better than m. I mean, you take 1,000,000, square root of m is 1,000 times faster. So square root of m asymptotically, you've gained. So this is the solution that these high-tech companies were expecting. And today, as I said, they moved on to other questions because everybody knows this question in Israel. So it's not, and I tell my students that if you interview in some company and they ask it to you, don't go work there. It means they're not up to date. Okay, so this is now, to be honest, they actually asked something a little bit more sophisticated in some sense. They didn't use n. They said, well, you have 100 floors, and they wanted an exact number of throws that you do. So you say, well, a square root of 100, but no, it's not exactly a square root of 100 because it's 2 times the square root. And you can do better than 2 times the square root because notice that the longer you go up, the more you've expended of your first square root. And so the idea is to make the first blocks a little bit bigger, and the size of the blocks becomes smaller and smaller as you go up until you reach an equilibrium, which is still asymptotically O of square root of m. But if you look at 100 or any such number, it comes out to between square root of m and 2 times the square root of m. Now, if you want to, you can actually figure this out, put in the formula and say, this is k is the number of throws that I threw for the first ball, and j is the number of throws for the second ball, and you want to and do your derivative there because you want to minimize the total number of the function there. It's going to be still something between square root of n and 2 times square root of n. So as far as a theoretician is concerned, I don't care, but I'm saying that in the when they asked the question, they actually cared about also the fact that people would observe that you can get a smaller constant, because I don't know, high-tech companies think that the constants matter. So, which is something I don't, but they do. So they ask it that way. But let's leave these companies alone. Now, this is the story that I wanted to tell you, that in some sense, what we got here is a bounded divide and conquer. It's a divide and conquer, but you can't go all the way down. In a divide and conquer, you make an experiment, you cut something, and then you keep going, and you cut again, and you keep going. You can go indefinitely. But if you can't go indefinitely, because you only have a small number of tries, then you don't have a log anymore. But at that point, according to the number of tries that you have, you can still split it in some sort of a divide and conquer way that is better than linear. And so that's where we got the square root of m. Now, the meaning of the two balls in our case, as I said, it's a bounded divide and conquer, but the meaning is that in reality we have different paradigms here. And what we have is we're going to look at two different algorithms. One that works on large groups and one that works within a group. So the two balls, in our case the balls are identical, but in the story the balls are identical. But in our case, where we're going to be using this kind of idea for our pattern matching, the balls are going to be different kinds of techniques. We're going to have a specific techniques that works well on the groups and will give us a good, efficient solution. And then we'll have a different technique that knows how to work well inside the groups, in the small numbers. So that would be the second ball. But together, between the two of them, we're going to get the square root. So because you have the square root, so you already know that what we will end up having is not O of nm, but it's going to be basically O of n square root of m. But in particular, what we'll show is that we can find all the mismatches we can count all the mismatches, even for infinite alphabet, in time big O of n times the square root of m log n. So this is where we're going. And this is definitely better than O of nn. I should also say that it's still an open problem about whether you can do it faster than that. And so anybody who wants a quick PhD, go home tonight, figure out a faster algorithm for counting mismatches than O of square root of m log m, come back with it, publish it, and you're well on your way to a PhD. A master's for sure, but probably well on the way to a PhD, because we count like 3 papers as a PhD, 1 paper for a master. So that's the... Now, I think that if anybody proved the P and NP problem, even if it's 1 paper, he would probably get a PhD in our university. So it's not hard and fast, but it's like, in general, it amortizes to 3 papers for a PhD and 1 for a master. So here I gave you all a challenge. All right. Okay, so this actually shows things that we've done, but let's repeat, especially if not everybody understood. So convolutions is going to be what works for large groups for us. And large groups, what do I mean by large groups? It means that in the pattern, if we have a symbol A that appears many, many times, I can still count all the mismatches of that symbol A in time n log m. I don't care how many times it appears. It can occur, like, half of the pattern could be A's, and I still would work the same amount of time. So the convolutions work well for large groups. And now I remember that there's also a very nice animation here. So what you have here, and that shows you why the convolution is important to us, if you put the B0, B1, B2, you see that that's like right, that column is exactly how you want it, and then the second one, and then the third one, beautiful. And we can do it in time O of n log m using the FFT. Okay, now, our solution was to reduce it to a Boolean integer or real multiplication. So even though this had a nice animation, I didn't use this because, as you see, it went really fast over this entire reduction to multiplication. And I felt that if I'm just going to say, okay, so it reduces, it would be pretty bad. So that's why I showed the other slides. And as we say, the reduction costs, and we're going to see now why. But the nice thing here, I think it needs to go down a little bit more. we're going to be doing something else now. We're not going to be counting mismatches the way we counted before, but we're going to be counting matches. Now, I claim that counting matches is really no different than counting mismatches, because if I give you an algorithm that for every location tells you how many matches there are, and my pattern is of length m, then can you figure out how many mismatches there are? M minus the number of matches. So telling you how to count matches is really not making anything easier for myself. It's just methodologically going to make it easier because I can explain the algorithm in an easier fashion. So when I say that what I want to do is count mismatches, and you should also know at this point I can throw in this new word, the Hamming distance of two strings is the number of mismatches between them. So this is called the Hamming distance. There are many string metrics to count the distances between strings. This is probably the simplest, most basic one, and that's the Hamming distance. It's the number of mismatches between the strings. So what we want to know is find the Hamming distance. In fact, we're going to do the opposite. We're going to find the number of matches, not the number of mismatches. So the example we don't need to see because we saw already, but similar examples, but it's very nice. And this explains the reduction that we finished the last class with, and that is that we'll take the text, multiply it by the characteristic function of a. But here's the difference, because what we're doing here is we want to count matches, not mismatches. So whereas before we multiplied the text by the complement of the characteristic function, since we're counting matches, we're just multiplying chi-ap times chi-apr. Because what we want to count is all the a's of the text that match a's in the pattern. So what we're going to do is all the a's in the texts are going to be 1. All the a's in the pattern are going to be 1. And when we multiply them, it basically means shift and count all the clashes of 1 and 1, which means we count all the 1s in the pattern that match 1s in the text for every shift. So same thing as we did before, except since we're counting matches rather than mismatches, so we have here the characteristic function everywhere rather than the complement. So far, we haven't said anything new. And we know that for an alphabet with a fixed number of symbols, it's O of n log m, and the problem is infinite alphabets, and that's where we are. Now, we also know, and that without loss of generality, we can say that our alphabet is of size no longer than n plus 1, even if it's bigger. And here you see a very nice example that shows that if the text has all kinds of letters, all the letters that are not in the pattern, replace them by a single letter, and you'll have the same number of matches or mismatches. So your alphabet is of size n plus 1. So far, so good. Now here's a wrong divide and conquer idea, and because it's wrong, I'm not even going to get into it. It's a little educational to think about, but let's skip it. But what we need is a faster way to compute matches of x to itself. And the faster way that I'm talking about is now going to be the other side. So our first method that we said is the method that deals with the large groups was, we said, the FFT. So you multiply the FFT by you multiply the pattern by the text, and you take a symbol and you count all the matches of the symbol. If that symbol occurs a large number of times, still in O of n log m time, you've counted all the matches. But what happens now? Think about the other side. Think about the number x that appears in the pattern a very small number of times. It appears a constant number of times. Let's say C, let's say 3, I don't know. You have an x that only appears in the pattern 3 times. Can I count all the matches of x in the text? faster than by using an FFT. I mean, if I use an FFT, obviously the time is going to be n log m. Can I do it faster than n log m, knowing that x only appears 3 times? So we need a different algorithm. It's not going to be the FFT. It's going to need to be a different concept. We need to think differently. And the algorithm is going to be the following. The algorithm is going to be it's even going to be the naive algorithm in some sense. But the naive algorithm, looking at it from the other side. What does the naive algorithm say? The naive algorithm says that here's the text. The text it starts there, it ends there. And I want to know, and every location in the text, I have a bin. And in this bin, I want to know, what I put in the bin is all the errors. How many mismatches I have for the pattern that starts in this location of the text. So the naive algorithm is going to say, okay, come to this place. You need to fill this bin. How am I going to fill it? Let's take the pattern and match it. Does it match this? Yes. Does it match this? Yes. Does it match this? No. Okay, so I have 1. So I keep 1 mismatch. It matches, matches, mismatch. I now have 2. So I go back to where I was, and I put these 2 errors here in this bin of errors, and I know that in this location I have 2 errors. Then the naive algorithm says, okay, so now move over 1 and do the same thing. So match, run, and match all of them, run back, and put it in the bin. And so you see there's a lot of running back and forth here that I'm doing, and that is why the time is going to be O of nm. Now, if I want to find the matches, the number of matches of x, and I do it that way, I'm not really gaining anything. Because I'm still, so I have my x, and I'm going to say, are you an x? Are you an x? No, no, no. Ah, this is an x, and this is an x. So I have 2 of them, and I still need to run down and put the x. So I didn't gain anything by the fact that I have x that only appears once with this naive algorithm. I'm still working O of nm time. But now let's think differently. Let's look from the other direction. Let's look at the text and not at the pattern. So if I'm sitting here in the text, suppose it's a beach, and I have my chair and an umbrella, and I'm drinking and I'm sipping soda and looking at the beach, and I really don't want to move much. But people are asking me, is to find these matches of the x. And they say, well, can you help? And I'm going to say, how can I help? Well, I'm looking at what's written in the beach, and it's not an x. So I say, well, it's not an x. I can't help you. But that's good. If it's not an x, then no one needs that information anyway. But what if I look down and I say, well, it is an x? I can help you. It's an x. Well, who can I help? Which bin is the one that needs to know about this x? And let's assume that x only appears once in the pattern. So the pattern was, I will draw the pattern for you. The pattern was ABC, ABC, X, CCB, AA. Okay, so this was the pattern. Now it so happens that here I am sitting on the beach with in my hand this glass and drinking, and I tell them, okay, people, well, you wanted to know about x? I have an x for you. Which of the bins should be updated? Who should get this x, this number from this x? Obviously, this bin, right? So if this was the text, okay, I'm on the text. I don't know what the text is, but I know that this is the pattern. So if I have an x, x only appears once in the pattern. This x can only help a single location. It can help this location. So if it is counting how many matches do I have of x, then it now knows that it should be updated. This x cannot contribute anything to anybody else. Why? Because it doesn't appear anywhere else in the pattern. Okay, is it clear? The x is not, this is the only place in the pattern where x is. It's not anywhere else. So, who, when he goes and counts of these guys who work O of NM, which one is going to be able to actually say, well, I have an x here? Only this guy. If he's going to start running and looking for the x's, he's going to find this x and he's going to put it down. But this guy is not going to find an x because the pattern is going to be shifted. And this is not going to find an x. None of them are going to find this x. The only collector who collects his x that is going to find this x is going to be this one. Nobody else is going to find this x. It doesn't match anyone else. I'm now counting matches. Yes. So what I have there is the pattern. I don't know what the text is, but I do know that there's an x in that text location. I don't know what's in the other text locations, but here there's an x. So what it means is that if x is in, this is 1, let's say 0, that's easier. 0, 1, 2, 3, 4, 5, 6. So if x is in index 6, and I am in the text of the pattern, and if I am in the text in location I, then I go to I minus 6, and I say to them, put in your bin a match. I'm going to do this for every I in the text, but right now I'm concentrating on this particular I, and what I'm trying to do, the point I'm trying to make is that everyone understands that this x is no good to anyone except for bin I minus 6, because that's where there's going to be a match. No one else is going to find a match with this x because it only appears once in the pattern, and that's where it appears, in index 6. Okay, fine, so that's good, but this was one position. So I was sitting here on the beach, and I say I can help with the x. So how much time do I work? I yell, okay, you I minus 6, put a match. So he puts a match in I minus 6. Now they say to the guy next to me, can you help? He says, no, because I don't have an x. And the guy next, he says, no, I don't have an x either. And the guy next, well, I have an x. And I'm already in J. So, okay, you in J minus 6, put a match. And you go on. So, we went through the entire text, from 0 to n. How much work did we do for every location? O of 1. Because every location just yelled and said, you, in my location minus 6, add. And we're done. So, this algorithm, in fact, in time, big O of n counts all the matches of x. Whereas if I wanted to count all the matches of x in the naive way, it would be O of nm. And if I wanted to count them by FFT, it would be O of n log m. But this is faster, because x only appears one time. But here I'm saying, suppose that x appears c times. So, fine. So these are the 3 times that x appears in the pattern. We do the same thing. I am sitting here on my beach chair, and I find an x. So I yell, okay, you in this index, you can say that you found an x. But x appears 3 times, not 1. So I'm going to yell again. So you here, you also update your matches. And you here also update your matches. Okay. So how much time does our algorithm work? N times c. Which means that as long as a symbol does not appear in the pattern more than log m times, I am certainly faster for counting that symbol than the FFT. Now, not only that, it means something else also. It means that suppose I have a pattern, we now have the other side of the coin. So one side of the coin was where the pattern was composed of 4 symbols. And if it was composed of 4 symbols, we count all the errors of all these 4 symbols each one of them n log m time. So in O of n log m times 4, we counted all the errors altogether. Now the other side is, no, we don't have 4 symbols. We have a lot of symbols. And not only do we have a lot of symbols, but no symbol appears more than 3 times, because we have so many of them. So the most that any symbol ever appears is 3 times. Then what can I do? The same algorithm, but not just for x, because who cares about the x, okay? Whatever I am, whatever symbol that I have, this particular symbol only appears 3 times. That's the most that anything appears. So I look at my symbol, I keep a list of the indices of my symbol, and I yell, okay, you, in this and this and this, update. You go to the next one, it's a different symbol, but it doesn't matter. He has a list of the 2 indices that his symbol appears. So he said, you update the 2. You move to the next one, he only appears once. He says, you update the 1. Then again, we have 3 times. So update the 3. But the point is that if we have lots and lots and lots of symbols, and all of them appears at most c times, then our overall algorithm is going to be O of n times c. Because we're going to go on the text, and each location is only going to work c times. Okay? So beautiful. So now we have to balance the 2 situations. We have on one side the ball that knows how to handle the blocks. In other words, things that happen many, many, many times. We have on the other hand the ball that knows how to handle things that are within the block. They're like the little ones. Those are the NC. So what would be the general idea? Let's think a minute about how your general idea would be, and then we're going to see the details, because the details are very elegant. I want to tell you also that this algorithm is called the Abramson-Kossaraju algorithm, because in 1987, Carl Abramson published this as a paper in SciComp, and in that year, independently, Raul Kossaraju sent a paper that was accepted to stock that gives more or less this. I mean, the idea is the same idea. None of them is worded the same way, because they were very complicated. They didn't see that what's happening here is these 2 balls. But think about the fact that we've been talking now with stories and everything about 45 minutes, a bit less, and I'm close to the end, and this is all the details that you need for a stock paper or for a SciComp paper. I mean, this only shows you how, with years, an understanding of a problem, of what's really happening there, really helps to somehow, all of a sudden, make something that used to be extremely complex and very few people understood what's happening. All of a sudden, it's so clear. And what's clear here is that we need to balance 2 cases. We need to balance a case where we have an FFT that knows how to work on large groups of occurrences of a symbol in a pattern, and versus the algorithm that knows how to work on symbols that appear a very small number of times. So think about how you can balance these 2 things in general, because in general, you could have some symbols that appear a few number of times, and some symbols that appear a large number of times. So how are you going to balance it? And you already have a hint, because you know that with 2 balls, you have a square root of n running around there. So now you have all the information. Think about it, and you'll have figured out the SciComp paper. Do we have a winner? Well, the high-frequency ones, we do an FFT. That, in 1 n log m, you count all the occurrences of the high-frequency one. But see, There it is. She has it. Say, take all your, okay, this is not the details because we're not going to get to the final best solution, but it's going to give you already the idea. So let's look at the symbols that appear more than square root of n times. Square root of m times in the pattern. How many such symbols could we have? No more than square root of m, right? So the symbols that appear no less than square root of m. So they appear at least square root of m times. There are square root of m such symbols. So each one of them, count all of their appearances by FFTs. How many FFTs do you need? Square root of m, because you have square root of m such symbols, right? So you have square root of m FFTs, and each one of them counts the number of occurrences of all the frequent symbols. Put them in the bins. Now, go to the infrequent symbols. The infrequent symbols, how many times do they appear? Less than square root of m times, right? So it means that the list that every guy sitting on his beach chair that he has is no longer than square root of m. So if you run through n, and each one of these guys works square root of m times, you're going to, at the end of this process, count all the infrequent ones. And now you're done. How long have you worked? Square root of m times n log m plus n square root of m. So there's a bit of a slack there that we want to fix, but which we will. But in general, already you have an algorithm whose time is O of n times square root of m times log m. That's better than the naive, okay? So you did it. That's a SciComp paper that you just figured out. No, but you have to figure out who is high frequency and who is not, because then you need to look at the low frequency elements and give the list of indices for each one of them. But that's still O of m log m time at worst, which the log you can throw in. It's there. Yes, so you need to figure out the threshold, and that's what we're going to see in a minute. But we saw that if we take square root of m, we're done, in some sense. It's not as good as what I promised, because what we saw was n times square root of m times log m, and I am saying that what I really want is n times the square root of m times the square root of log m, which is even faster than what we just figured out. But it's close enough. So the time here is O of nc. So as we said, the trade-off is that if x appears in the pattern, so we want to find out this threshold exactly that Professor Misra is looking for. So let's assume that that threshold is c. Okay, so if x appears in the pattern more than c times, we're going to count the matches by the FFT, and that is going to happen in time O of n times log m per x. And all the x's that appear less than c times, we're going to count the matches simultaneously in time O of n times c, for all of them. Because these are all the x's that appear less than c times. So now we have to figure out what is this c, what is this threshold. But that's easy to do, because how many elements appear at least c times? It's m divided by c. You can't have more than that. If every single element appears exactly c times, you have m over c elements. If some of them don't appear at that time, or if some of them appear more, you're going to have less. But this is the maximum that you can have. So for these elements, the time is definitely O of m divided by c times n log m. For the others, we know that the time is O of n times c. Okay? Now, we need to find out the trade-off. And my claim is that the trade-off is easy here, because the higher the c goes, if you make c bigger, this becomes bigger. But then, this becomes smaller. And therefore, what you want is the c such that they're equal. Because if the C goes higher, one of them is going to be below. And you want to optimize. The optimization is going to be the sum of the two. So when they're equal, you're done, because then after the equal, every perturbation is going to make it worse. Because although it's going to make this less, it's going to make this more. So you're going to lose. So your threshold is going to be when these two are the same. So what do we want? Mn log m divided by c is equal to Cn, which means that m log m equals c squared. So Einstein says E equals mc squared, and we say m log m equals c squared. So this is our answer to Einstein. And if that's the case, then c is equal to square root of m log m, which means that these are equal. If c is equal to square root of m log m, then your time is O of n times the square root of m log m. And that's the best threshold, the best you can do by the current knowledge. And the current knowledge that we have is that of all the different algorithms that we have, we don't have a divide and conquer algorithm for Hamming distance. But we do have a bounded divide and conquer, and that's why we get this. This does not, it's not a lower bound, obviously, so why should that be the end? Maybe you can do pattern matching in the Hamming distance in time less than O of square root of m log m, which is the challenge that I left for you. But this is the Abramson 87 algorithm and the Kosarajo 87 algorithm. So that's their algorithm. Okay, how the mighty have fallen. I mean, an algorithm that few people understood at the time. Really, I mean, you read that and they said, wow, how did it work? But this is it. This is what it is. Now, this is kind of a good... so in our tower metaphor, what we had was we did a separate convolution for each group of floors. Those are the ones that are big. And then the elements within the group were taken care of individually. So that was in our metaphor, and that's why the square root of m somehow got there together. Now this is more or less a good place to break, but because but I'm going to say one thing. I wanted to give a few examples of where this idea of the bounded divide and conquer actually worked. And one of the examples is going to be in computational biology, as you can see. Now, the reason that this slide is here is the following. In 1995, there was a big conference in Padova of computational biology. At that point, what we know as computational biology wasn't such a big field with so many people in it. It was really a very young and fledgling field. Not too many people were doing it. But we already recognized that there's something there. And so the decision was to grab a bunch of people from pattern matching and a bunch of people from computational biology, bring them together to a nice place like Padova, and Padova is a nice place, and sit there for a few days and talk, and each one will present their problems and see how we can enrich each other and to live a full and fulfilling life. So that was the general idea, and kind of that was one of those starting conferences of bioinformatics, and I mean, Recomb wasn't there. None of these things was there. This was the beginning. So the beginning isn't that far away even. But something funny happened. In those days, there weren't these projectors and the computers. 94 were certainly, we didn't have the PowerPoint and all these things. In 94 wasn't there, and people still used the old projectors where you put slides on. So I don't know if you even saw this, any of you, but there was this projector. You write on a piece of transparent plastic, and you write with a pen, and then you put it on the projector, and it projects it, and lo and behold, you have something on the wall, which was the height of technology at some point also, because before that we wrote with a white chalk on a blackboard. So technology advances. So in those days, everybody came with their slides and transparencies, and and we put it on the projector. It turned out that the biologists, it was marvelous, because they would come, they would have these beautiful pictures of proteins folded in 3 dimensions and things like, I mean, this is a pretty picture. They would have these beautiful pictures, and they would put them on and say, here, you look at this picture and you right away see the challenge that we have. And so it was great. And then would come the pattern matching people, and they would put the slide that says, let T be T1 through Tn be a text, and P be P1 through Pn be a pattern. And it was pathetic. It was really a bit pathetic. It was pathetic for another reason. A friend of mine from cryptography said to me once, you know, you all do the same thing. I come to a conference and somebody comes up and says, let T be text T1 through Tn, P a pattern P1 through Pm, and I fall asleep and I wake up at the end when everybody's clapping, and it's the same talk. You're giving the same talk. And I said to him, yeah, I know exactly what you mean, because when you guys talk, it's also the same. I mean, you say, well, here is Alice and Bob, and they have a secret, and here is Eve, and I fall asleep, and I wake up when they clap. What do you want? So the pathetic thing was that we had these slides that were just nothing. So somebody had the brilliant idea. They took the most beautiful transparency that the biologists had, and they left it at the table there. So every computer scientist that came up started out by putting that slide on, and he said, look what a beautiful slide. Then he took it out and say, now, let T be text T1 through Tn, and P be a... Now, in honor of that conference, I have this, because it has nothing to do with what I'm trying to say, but I'm going to now build a problem, bring a problem that actually uses the techniques that we talked about, and the problem actually is related to computational biology. So I said, okay, look, computational biology, it's really pretty. And now the problem that we're going to look at is the following. Weighted sequences. So we assume that we have T, a sequence over alphabet, this, and go on from there. So, but since we only have 2 minutes left till 1:30, let's actually talk about this tomorrow. And this was a heavy day, I know, a lot of new concepts. So let's stop here. Try to let these concepts settle in, because what we're going to do tomorrow is use these concepts in all kinds of flexible ways. So even go over it, make sure that you understand the main thing, the key idea that says that the FFT, what it does is it allows you to clash two things, and then you count all the ones that match with ones. And you do that in n log m time. That is like the big hammer there. Another thing to keep in mind is that whenever you have some technique that deals with big numbers and some techniques that knows how to deal with things that happen very infrequently, you can somehow put the two together and get a square root of n advantage. So we're going to use all of these in all kinds of problems that actually come from the real world, from biology, from other areas. And so let the ideas gestate in your mind, and because they're not hard, but they are new. So be comfortable with them, and then so tomorrow, when you think about it, I will even let you think about a little bit with every one of these problems. It can be kind of like the tutorial with every one of these problems, and see where, if you come up with how we're going to do it, even if not with the details, at least to come out with the idea, because this is how research is done. You have your concepts that you know, you have a problem, you apply the concepts, it doesn't exactly work, how do I change them so that it will? So that's what we're going to do tomorrow. Have a great afternoon, and we'll meet then.